Alright, so last time I started to discuss a invariant for three manifolds, compact oriented three manifolds, and I want to continue this discussion. So let's recall the situation. So let's say MG is a compact oriented three-dimensional Riemannian manifold. And I will apply the theory to the Levi-Civita connection of the metric. I could also sort of work with connections, not without metrics, but it's convenient to do it this way. So my connection number 0 will be the Levi-Civita connection. And now, there are no non-trivial characteristic classes on the tangent bundle that we know, and in fact the tangent bundle of this manifold is trivial. And but even if it wasn't, the Pontryagin class would not have anything in degree 3, nor one Euler class. So the question is, how can we come up with an invariant anyway? And in order to do that, we, instead of looking at the Pontryagin class or its representing forms, we realized that since the Pontryagin class is 0, the representing form must necessarily be exact, simply by reasons of degree. First Pontryagin class is of degree 4, but we have a 3 manifold. So the transgression form that compares it, the thing between two different connections, is then a closed form and therefore represents a cohomology class. So why not take that one? And that's what we did. And in fact, so we are interested in an invariant for the Levi-Civita connection, but we need, for the transgression form, we need a second connection. And for that, we used a flat connection, which we get by trivializing the tangent bundle and pulling back the canonical flat connection on the trivial bundle. So that's a flat connection. Induced by a trivialization. Tangent bundle. And now, okay, so the tangent bundle of a three-dimensional oriented manifold or equal manifold is always trivial. So now we have a metric, but then the tangent bundle being trivial means I can find a global frame field on that manifold. And then, since I have a metric, I can apply the Gram-Schmidt procedure to this frame field, which at each point is a basis, and therefore obtain an orthonormal positively oriented frame field. And I want to take the trivialization which is induced as by such. This means I can trivialize the tangent bundle as a Riemannian vector bundle, not just as a vector bundle. So any vector bundle which is trivial as a vector, or any Riemannian vector bundle which is trivial as a vector bundle, is also trivial as a Riemannian vector bundle. Meaning I can find a global frame field which is everywhere orthonormal, simply because I can apply the Gram-Schmidt procedure. So that's what I want to do. I want to, and this gives then, if I take the corresponding flat connection, this gives me a metric flat connection, which is metric. It's not torsion free, of course. All right, and such a trivialization, alternatively, as I just said, is given by a global frame field, so by the global section of the frame bundle, and the frame bundle that I'm using is the bundle of positively oriented orthonormal bases. Section of the SO3 bundle, SO3 principal bundle of positively oriented orthonormal tangent frames. And maybe I call this global section S for later reference. So this associates to each point of the manifold a positively oriented orthonormal basis. All right, good. And we started with the Pontryagin class, so the first Pontryagin class, which is represented in terms of curvature by an invariant polynomial, and the polynomial we determined, namely earlier, namely the polynomial p of x is given as a certain factor times the trace of the matrix. Last time we computed the corresponding transgression class. So, and what we want to do is is the integral over the manifold of the transgression form for these two metrics. That's a 3 form, so we can iterate over 3 manifold. So is this an interesting invariant of the Riemann manifold Ng? Okay. And well, so this choice of flat background metric is of course arbitrary. And if we want to answer this question, we must investigate to what extent this integral depends on the choice of flat background metric number 1. So that's what we need to do. So what's the dependence on the choice of this nabla 1, this flat background metric? All right, so let's just pick another one. So let S tilde be another global section of this bundle here, and let nabla 1 tilde be the corresponding flat connection. Flat metric connection of tension. So now we have 3 connections working around. So the connection we are actually interested in, the utility connection, and 2 flat reference connections, nabla 1 and nabla 1 tilde. Right, so we have computed this term, in fact. So we have written down a formula for it. And so what we found was that this transgression form could be written in terms of connection on curvature matrices as constant times trace of the following expression, omega 0, so the connection form of nabla 0 minus omega 1, connection matrix of nabla 1, wedge capital omega 0, curvature of the Levy-Chivia connection, plus 1/3 of omega minus omega 1 cubed. All right, and things simplify if we, so in fact here it's convenient that we can actually use a global frame. So usually these expressions were only locally defined, right? Because we only locally could find frame fields and express our connection and curvature in terms of these bases, local bases. However, now we have global bases, namely S, and we use that to write this down. And so this is a globally defined form on the nodes without any invariance considerations. But we have to compare this now with the corresponding thing where I replace omega 1 by omega 1 twiddle. It's convenient to choose one of these 2 frames, either S or S tilde, to do the computation, because then the corresponding nabla 1, little nabla 1, omega 1 will disappear. Because with respect to the induced connection, these sections are parallel. Okay, so let me do the computation with respect to S. So with respect to S, then this simplifies because the little omega 1 disappears. So this will then be 148 squared 0, which capital omega 0 plus 1/3 omega 0 cubed. And the other one is also computed with respect to the same frame field, so that the omega zeros don't change. So, but then of course I have to keep the omega 1 part, because the tilted frame is of course not parallel with respect. Now the untilted frame is not parallel with respect to the tilted connection. So for that I have to keep things. Then I have omega 0 minus omega 1 tilde, which curvature plus 1/3 omega 0 minus omega 1 tilde cubed. Alright. And so we want to compare these two expressions, so let's subtract. And see what we find. So the integrand, so maybe I put this factor, prefactor in front, so that I don't have to carry it around all the time. So the tilde here, and yeah, non-tilde here, so then let's look at this expression. So I take this expression minus that expression, and I just expand this expression. So this is multilinear, right? So I just expand everything. So then what I get is the trace of what? Well, so the first so the first term gives me a little omega 0 wedge capital omega 0. But this is cancelled by this little omega 0 wedge capital omega 0. So this goes away. So here I'm only left with minus little omega tilde 1 wedge omega 0. Okay, and then now I have to expand this cubic term. And then I have one term where all little omega zeros are cubic and no appearance of the tilde term. But this is again cancelled by that term. So this is not to be considered. Then we have terms where the omega 0 is quadratic and the omega tilde is linear. So those I have to keep. So that would be plus 1/3. Now I have omega 0 wedge omega tilde 1 squared, but I also have omega 1 wedge omega 0 wedge omega tilde, and I have another term, namely omega 1 tilde wedge omega 0. So those are the remaining terms here. And now we have the terms which are quadratic in omega 0 and linear in omega tilde. And okay, the linear omega tilde, then I have to be careful with the sign here, so I get a minus. So then I have omega 1 tilde wedge omega 0 squared minus omega 0 wedge omega 1 tilde wedge omega 0 minus omega 0 squared wedge omega 1 tilde. And finally I have the term which is cubic in omega 1, in the tilde term, which gives me another minus omega 1 tilde cubed. And that's it. All right. Oops. Okay. So let's see if we can simplify this expression. All right. So we have J. So let me the first one I'll change for a moment. Now what we have here, for example, if there are these two terms and also that term, so these only differ by the order of the factors. So, for instance, I could bring them all in the form of this one. So, see how I did it here so that it's consistent. Yeah, so I could bring, so let's say, all with the tilde term in front, but then I would have to put this one in front, and here I would have to put this one to the back. I do have a trace in front, however, and so we have this formula: trace AB equals trace BA for all matrices, say complex value matrices, and therefore also for all elements or matrices with values in a commutative algebra. However, here these things are not really all in a commutative algebra because these are one-form value matrices. Up to now, when we dealt with characteristic classes, we always only inserted curvature terms which are even or degree 2 terms, and then everything was commutative. That's not so anymore, so we have to be careful. But the interchange that I have to make here is I have to interchange a one-form matrix with a two-form value matrix. And if you do that, then there is no sign still. Right? Because if you write this out, I mean, why is this true? Because you have, if you take the matrix multiplication, then you have Aij times Jk, so that gives you the matrix of the product, and if you trace it, then you'll have to take this double sum, right? And now if the entries of your matrix are commutative, then you can turn it around, and that gives you this equality. But that's still okay if these things commute, because this is a one form valued matrix, and that's a two form valued matrix. That's still okay. I can still turn around. So let's do that, because then these three terms give the same thing, which cancels exactly this 3 factor. So then I have plus omega 1 tilde squared, which omega 0. And similarly for the next three. So in this case, I can put the omega 1 tilde in front, put everything in this form by pushing this to the last term, and here putting this to the first term. So then we get minus omega 1 tilde, which omega 0 squared. And the last one stays as it is. So here I should not forget the pre-product 1/3. Now it looks a bit better, and the next thing that we use in order to simplify this are these structural equations which relate curvature and the exterior derivative. So we have this always, and for the flat connection we have the formula 2, but in this case, since it's a flat connection, the curvature is 0, so that gives us a direct, so that means I can replace any omega tilde square by a d omega tilde. So this is that. So here I use just this formula. Then I get minus omega 1 tilde, which d omega 0 plus, and then I get minus omega 1 tilde, which omega 0 squared. So that's the first formula, and for this one I use this formula, which then gives me plus d omega 1, which omega 0. And the rest remains. So minus omega 1 tilde, which omega 0 squared, minus this term. And now let's see. So wow, that's good, because this cancels already. And these two terms can also be combined. Oh, there's a tilde missing here. These two terms can also be combined, because by the Leibniz rule for the exterior differential, this is the same as d of omega 1 tilde, which omega 0. So that these are these two terms, and then we are left with that term. Okay, so it's getting simpler. And sure enough, This is a fixed linear map, so I can map this out. So that's d trace omega 1 tilde of 0 minus 1/3 trace of omega 1 tilde. And now what we want to do is we want to integrate the thing over the manifold. So we are interested in this term after integration over the manifold. Integrate this formula over the manifold, then we see that this term tops out by the Stokes theorem. So we are only left with this term. Stokes says after integration, the correction term between these two, for these two different choices of background metric, tilde here, is given as minus 1/3 trace integral over the trace of this cubic term. So that's what we have to understand better. So what is this term? Now one might be tempted to say that since we are here looking at trace of a matrix cubed, and remember these matrices are skew symmetric because we are working with orthonormal frames here. So the matrices, the little omegas and the capital omegas take their values in the Lie algebra of SO3, which is skew symmetric matrices. Now if you have a skew symmetric matrix, you cube it, then you get again a skew symmetric matrix, and the trace of the skew symmetric matrix is 0. But why is this not imply that this is 0? In fact, we would see that it's in general not 0. So if I had used this argument, you would have believed me, right? I could have told you, since, and then the reason is, of course, again, that these are not in a commutative algebra here. I could shuffle this one to the right side, sure, but this wouldn't change anything anyway. But I cannot conclude from the fact that this term vanishes for all scalar valued matrices, that it also has to vanish for these one form valued matrices. That's not a valid argument. So we have to be a bit careful here, more careful, and see if we can somehow find an interpretation for this term. So that will be the next step. And in order to find this interpretation, let me re-express this one form valued matrix that occurs here as follows. So we have, remember, so these two different, two different, let's say, I'm working with respect to a frame for the untilted background metric, but do this for the tilted induced connection. So if I write, so that's a frame field, so let me write it as E1, E2, E3, so these are three globally defined vector fields on my manifold, pointwise orthonormal and positively oriented. So that's my S, and the S tilde takes a similar form, of course. These are three different vector fields. These guys are parallel with respect to nabla 1, and these are parallel with respect to nabla tilde 1. And what this matrix here contains is the derivatives of these frame fields with respect to nabla tilde. So question, how do these things relate, these two sections? Well, they are both sections, global sections in an SO3 principal bundle. And on a principal bundle, the structure group acts simply transitively from the right. So at each point, the value of S differs from the value S tilde by multiplication of a uniquely determined matrix in SO3. I mean, that's clear anyway, because both of them are positively oriented orthonormal basis, so one is transformed into the other by a matrix in SS3. But this matrix depends on the base point, right? So then write S tilde, so how I do it. S as S tilde times H, where H is this function with values in SO3 of transformation matrices. Let me do it this way around. Okay. And now I'd like to express these omega tildes here in terms of this function S. Okay, so let's see. And well, so how are these entries of these matrices defined? I have to take, so we do everything with respect to the untilted frame. So I have to take, I have to take EI, differentiate it with respect to the tilted connection in some direction, and then express the result again in the same frame. J and the coefficient functions are then the connection forms for this connection evaluated on X with the entries on J. So this was the definition of connection. Good. Okay. And well, now I want to use this and express this EI in terms of the tilted frames, because those are parallel with respect to lambda tilde. Okay, so this is tilde 1 off. Now, what does this mean? That means that this EI can be expressed in terms of the tilde frame, some K tilde, and then we have here the entries of this matrix valued form, so which is HK. So that's what we have. So by the Leibniz rule, this is, well, we have these are just scalar valued functions. So I get initial derivative times EK tilde plus HYK nabla 1 tilde X K tilde. And now the good thing is that this is 0, because these frames are parallel with respect to numbers. So this term goes away. And in order to compare, I also have to do the conversion here. So then I have double sum over J and K. These coefficients first. And then I have to express this in the tilde frame in the same way. So that would give me H, J, K, E, K tilde. And now I can compare coefficients. And so we see that this connection form nabla of this matrix, nabla 1 tilde, can be expressed entirely in terms of the derivatives of H. So what we find is that the sum over J, so that's coming from here, of omega 1 tilde X H Kj is equal to this coefficient here, which is del X H, no, that should be what are the coefficients here? H I K, which is the same thing as saying, well, that's the differential of H I K applied to X. And so what we find, so here we have the connection matrix, here we have this matrix of H itself, this matrix multiplication, gives me the differential of the matrix. So this is omega 1 tilde of x times h is equal to dh of x, or in short, omega 1 tilde equals dh times h to the minus 1. So it's really this omega tilde occurring in the correction term that we are interested in. This term looks like a logarithmic derivative of the function that gives me the coefficient, the transformation matrices. Okay, in order to proceed, I have to make an interlude so that we understand what this form is, about a canonical form that you always have on any Lie group, and that's the so-called Maurer-Cartan form. On a Lie group G, and then we will apply this to the group SO3. For us, this will be SO3. And so how does that work? Well, suppose, so I'm claiming there is a canonical one form on the Lie group, which is of interest, and this is defined as follows. So choose basis, and we call it E1 up to En of the Lie algebra of G. Now we can extend this basis as to vector fields on the Lie group by either left or right translation. Let me do it by right translation. So put, and now the little e's are the right invariant extensions of these vectors in Lie algebra. Here I consider the Lie algebra as the tangent space to the Lie group as the unit element. And then, well, what can I do in order to define the vector field at a point G in the Lie group? I simply take the corresponding vector here, J, which is a tangent vector at the unit element, and then I push it forward with right translation to the right point. So what I do is apply the differential of right translation with the element G applied to this. So, G is the map from G to G, mapping an element G tilde to G tilde times G. So I'm doing a multiplication with G from the right. So this will map, in particular, it will map the unit element to G. So if I differentiate it, I get a map which maps the tangent space at the unit element to the tangent space at G. And so this is a tangent vector at G. That's called the right invariant extension of the elements in my Lie algebra. Okay, good. And what can I do with this? I want to write down a canonical one form. And in order to do that, so these are vector fields. So I have now globally defined basis fields here. I have a trivialization of the tangent bundle of my Lie group this way. And now let theta 1 up to theta n be the dual O-frame. So these are one forms, and at each point of the Lie group, this is the dual basis to this basis, by definition. And now the Maurer-Cartan form, omega G, is defined to be sum over J Ej, so these elements in the Lie algebra, tensor Ej. So that is a G valued one form. Okay, and you can check by hand if you want at this point that this does not depend on the choice of basis here. Because if you choose another basis, then the corresponding transformation will be corrected by the corresponding transformation that you have on the dual basis. However, we will see a formula for the Maurer-Katov form which is more invariant anyway at the moment. So we don't really have to do that. Okay, so yeah, how can we rewrite this Maurer-Katov form? You actually, in fact, usually the Maurer-Katov form isn't defined by taking left translations, left vector fields. I do this right, vector fields for a moment, we will see in a moment why. So you could do the same thing with left invariant extensions also. Okay, anyway, so now maybe can one write down this form in a different way without reference to some chosen basis? Let's see. So if we insert some tangent vector to our Lie algebra, to our Lie group into the form, so that is a tangent vector at some point G. And well, let's insert it. Then we have to apply theta j to this vector. And in fact, this guy I can express in terms of these vector fields by applying the inverse here, so which would just be the differential of rg to the -1. And so the right translation of g is inverted by right translation of g to the -1. So I can rewrite this as dr g to the -1 of the little eg at the point g times theta j of x, which is the same thing, and these are scalars now. This is linear, so I can put them in with the sum as well. So this is drg to the -1 of sum, and then I have theta j of x times ej. But now this is the dual basis of that one. And so that means the vector that we have here is simply x. All right, so good. And so that's another way. So see here, no reference to any chosen metric is present anymore. And now if my Lie group is actually a matrix group, like in the case we are interested in, you can still rewrite this in a somewhat different form. Namely, if we look at so let's look at the form. So if G is a matrix group, then the differential. So okay, so then dr g to the -1 of x, and let me write this as, so that's a tangent vector to the Lie group at the point G. So this can be written as the derivative of a curve which, let me call it g tilde of t, such that g tilde of 0 is equal to g. Okay, and so then you can write this as, insert this. And for now we use that it's a matrix group because then, okay, the chain rule first. This is rg to the -1 times that, so that would be g tilde of t times g to the -1. Now I'm using that it's a matrix group, and this is just matrix multiplication. And matrix multiplication, if I have a product of two matrices, one is depending on a parameter, you just differentiate that thing, and then you get x. So I can simply write this as x times g to the -1. Well, abstract Lie group, this doesn't make sense because this is some tangent vector, this is a group element. But if it's a matrix algebra, then we are just dealing with matrices here, both for x and for g minus 1, and then matrix multiplication makes sense, and this is what we get. So then we have that. So I could then, in the matrix group case, I could write this as x to the times g to the minus 1. And now, still in the matrix case, I might look at the form D. So at the one form dj times g to the minus 1 as a one form. And if I insert a vector x into that, then this gives me del x g times g to the minus 1. But the function g on the Lie group G is just the identity. And so this will be x times g to the minus 1. So that's how I want to write it. As the form dg times g to the minus 1 applied to the vector x. So that's the form of the Maurer-Cartan, or the formula for the Maurer-Cartan from on the matrix Lie group. Why? Well, because we have just encountered such a term. We briefly have computed. Where is it? It's here. So that's the kind of thing we just obtained for a function that is G group valued. So that shows us that this omega 1 tilde is nothing but the Maurer-Cartan form of SO3 pulled back via H. That's what we just. Okay, so that's good, because it seems to be related to some canonical object on the Lie group. And now let's see, what can we say about the cube? So we have to cube this term and trace it. So what do we get? So for that, I want to compute the Maurer-Cartan form of the SO3 using this original formula. Where is it? This formula. Good. And then, so let's start by finding the basis of the Lie algebra. SO3 basis. Well, that's not terribly hard, right? This is the algebra of skew symmetric 3 by 3 matrices. So let's just take E1 to be 0, 1, 0, 0, minus 1, 0, 0, 0. E2 0, 0, 1, 0, minus 1. And E3 I have to take 0, 0, 0. And I have to take 0, 0, 1. Minus 1, 0, 0. So that's the basis I'm using for SO3, for the algebra of SO3. And then I get this Maurer-Cartan form. So let's write it down. So the Maurer-Cartan form of SO3 is now, and I'm directly considering it as a matrix with entries in 1 forms. Then I have E1 times theta 1. This gives me the theta 1 here and the minus theta 1 here. And the rest is 0. And then I have to add E2 times theta 2, which gives me theta 2 here, and minus theta 2 here, and zeros for the rest. And E3 times theta 3, which gives me theta 3 here, and minus theta 3 here. So that's the Maurer-Cartan form. Okay. And that's being pulled back and then being traced. So, so that's what we're interested in. And so I can insert this. Pullback commutes with wedge product and also with this linear trace. So that's the same thing as H star trace of the Maurer cutoff cubed. So we have to compute this term now. Well, okay, so let's do it. So 0, theta 1, theta 2, theta 3, 0, minus theta 1, minus theta 2, minus theta 3, 0, times 0, theta 1, theta 2, minus theta 1, 0, theta 3, minus theta 2, minus theta 3, 0. And another time, so matrix is equal to, okay, that's 0. Theta 1 times theta 1 is 0. It's a 1 form, scalar valued 1 form. When you have a square, a scalar valued 1 form, I get 0. And theta 2 squared is also 0. 0, 0, and here I have theta 2, theta minus theta 3. Minus theta 2, theta 3. 0, theta 1, theta 3. Now here 0, 0, and here I have minus theta 3, theta 2. You have to be very careful that I don't mess up the computation. Theta 1 is squared 0, 0, theta 3 squared 0. Now here I have minus theta 1, theta 2. Plus 0, plus 0. Then 0, minus, minus gives plus. Theta 3 times theta 1. Plus 0. And here I have minus theta 2 times theta 1. Plus 0, plus 0. And here, minus theta 2 squared is 0, theta is 0, 0. And now times another copy of this matrix, which gives me what? 0. Here I get, so I have to be careful because this is multiplied from the right, right? This stands to the right. I can also put it here, and then maybe that's easier so that confusion is less likely. So then I can proceed as I wanted. 0, then I have minus theta 1, theta 3, 2, this term, and plus theta 2, theta 3, theta 1. And that's what we have here. And this term I'm not interested in. This term I'm not interested in because I'm going to trace it anyway. Okay, so this term I'm not interested in. So let's see this one. This gives me minus, minus is plus. Then I have theta 1, wedge theta 2, wedge theta 3. Well, for this one, that's 0. And here minus theta 3, wedge theta 2, wedge theta 1. From here. And I'm not interested in that one. Only this one remains, which is minus theta 2, wedge theta 1, wedge theta 3. Minus, minus gives plus, plus theta 3, wedge theta 1, wedge theta 2, for 0. So did I do it right? Okay, so now we have to trace the thing. Right? So what do we get? The sum of these three, and we see, I mean, this basically, so we always get some multiple of theta 1, theta 2, theta 3. We just have to check the signs. And here in this case, I have to do how many permutations to get it in this order. I have to just interchange these two. and that makes this sign go away. And here I have to put the theta 1 front, which makes two things. So the plus 1 persists. So that gives me 2 times that. Here this one is already in the good form, and here I have to put the 1 first, gives me 2 signs, and then I have to interchange that to give me yet another sign, which with this sign gives also a plus 1. So hopefully here it should be the same. So here I just put the 2 here, which cancels that sign. And here I put the 3 to the back, which gives me no sign. So altogether we get 6 times theta 1, which theta 2, which theta 3. So you see it's not 0. And in fact, that's really good, because this is essentially, that's a volume form. So I'm talking about a volume form on the Lie group, SO3. And so what we are really doing here is we take a volume form, so when I cube it and trace it, here, this is really a multiple of the volume form of the Lie group SO3 pulled back to the manifold. Good. And in fact, if I want to write this as the volume form with respect to which the volume is 1 on SO3, the vol of SO3, so that's the volume form with volume of SO3 in 1. So what I'm doing is I declare the basis that I started with to an orthonormal basis. And I do this at each point, so this way I induce a Riemannian metric on my Lie group. And then it makes sense to talk about its volume. And I do this with respect to the choice that I've made here. So these are orthonormal basis vectors. And then I want to write it, so that's certainly a multiple of the volume form, but which multiple? For this we need to know what is the volume of SO3 when we integrate with respect to this metric. Now SO3 as a manifold, it's RP3, it's just S3 modulo Z2, it's a real projective space. And by the invariance of the metric, it's a constant curvature metric, so it's just the quotient of the standard metric on S3. The standard metric has volume 2 pi square, I hope, in 3 dimensions. And so RP3 will have pi squared. So in order to get this volume form, I need to, so this has length 1, since it's orthonormal. So if I integrate this, I get the volume. So in order to get the volume form, I need to divide by the volume. So this one is divide by the volume, which is pi squared. And this is 6, right? So this one has length 1, this is an orthonormal coframe. If I integrate it, I get the volume is pi squared. Okay. So, all right, that's good. Because now we find an interpretation of this last correction term, of this space term here. If I integrate this, I get the volume. Okay, which should be pi squared. Yeah. Okay. Yeah, that's true. Yeah, that should be right. So this is now normalized to 1, right? Okay. Therefore, let me write it like so. This expression is 1 on 6 pi squared times the volume. That's what I want. That's actually what I wanted to say. So the volume 4, no, not the volume. The volume form with respect to which I get 1. Now if I integrate this one, I get pi squared. Yeah, I get pi squared. If I integrate this, I get 1 So the 6 should go, yeah, like this. I mean, the 6 has not, I mean, this is of length 1. If I integrate it, I get the volume. If I integrate this, which is pi squared, if I integrate this, I get 1. That's correct. Anyway, okay, so that's what we find. So let's see. So this correction term, trace of omega 1 tilde cubed, as we just found, turns out to be integral of what? Of this pullback, h tilde trace of the Maurer-Cartan form cubed. And this we have computed to 6 times that, which is pi times square the volume form. So we get 6 pi squared integral over m h tilde of the volume form of SO3. Okay? So this now should be right. And now if you have a map between two manifolds, in this case we have two 3 manifolds, namely the 3 manifold M and the 3 manifold SO3. And we have this map H from M to SO3. If I pull back the volume form with respect to the map and integrate, what do I get? So this is a well-known number. Exactly, it's the mapping degree of H. All right. So let's see if I look at the difference between, that's what we were interested in. And then we saw that this is, what was it, 148 pi squared. It was minus sign, I remember. Minus sign doesn't matter anyway. So then we have so we've found that this is 1/3 of the integral over the trace of this term. There was 1/3 in the formula. And now I can insert this one, which gives me minus. So the 6 cancels the 3 and makes this into a 24. Integral times the degree of h. So that's a correction term. And of course, this correction term can be non-zero, because you can choose, you can prescribe the function h if you want. You just you can pick any function of any degree, and for your second frame, you just take the corresponding S tilde. The pi square should cancel too. That's true. With this one. That's right. Yes. So, so the difference is not zero in general, but the point is that this number is always an integer. So that's really the key observation. So that means if we multiply by 24 and integrate the transgression form with respect to any flat background metric, we get a number, and this number is independent of choice of background connection modulo z. So if I take this not as a real number, but as a number in R modulo z, then it's well defined. Or then it does not depend on the choice of number one. So I take here the residue class of this number in R modulo z. So this is independent of choice of number one. And so we can call this invariant, and so it depends only on the Levi-Civita connection of the manifold. So it's an invariant for our Riemannian manifold. And that's the Chern-Simons invariant. Good. So that is the Chern-Simons invariant. And now, maybe let's look at an example. And as an example, I take SO3 itself, which is nothing but RP3. RP3 is orientable as a big group. So one always has the idea real projective space is not orientable, but that's not true. It's only even dimensions. So that is a perfectly fine choice for my 3 manifold M. And now I take it with the standard metric, so with the round metric coming from the standard metric of S3. So with sectional curvature K-1, so that volume is pi squared. And now, what is its Chern-Simons invariant with this metric? So with metric G, with the standard round metric G. Okay, so we have these orthonormal fields that we have introduced earlier. It's a global orthonormal basis. And in order to compute it, we somehow need to find the connection form of the Levi-Civita, the connection matrix of the Levi-Civita. Right? And so how do we do that? And for this, since these are vector fields which are related to the Lie group structure of SO3, there's a convenient way to compute that. Namely, if you want to compute, there's the Kosovo formula for the Levi-Civita connection, which tells you that if I take nabla EI, EJ, EK and take its scalar product 2 times, then the Kosovo formula expresses such a thing with 3 vector fields here in general on a general Riemannian manifold by 6 terms. 3 of these terms involve taking scalar products of 2 of these 3 vector fields and then differentiate this in the direction of the 3rd vector field. But these will all vanish because this is the orthonormal basis. So the scalar products will be constant, 0 or 1, and if you differentiate, then you get 0. And then there are 3 more terms which involve Lie brackets. And the good thing is that these Lie brackets can easily become computed from the Lie brackets of our basis. And so to get the signs right, let me write it down. So this is minus Lie bracket of EJ, EI multiplied with EK minus E1, EI, E2 multiplied with this is the opposite. That's correct. And then here we have first one here, and here we have EK, J, minus, and the last one will involve EI here, and then here we have EJ and EK. Okay, that's the formula. If I'm putting mess up the signs. Now, these come from right invariant, from right translation of this particular basis of my Lie algebra. And of course, for these things, I can compute the Lie brackets. Let's do that. And insert it in this formula. Good. So let's see. The Lie brackets are simple in this case in the sense that if you take the Lie bracket of 2 of them, you always get a multiple of the other one. So what you get? This matrix times that one. So now watch closely if I do it right. 0, 0, 0, 0, 0, 0, 0. Now 0, 0, 0, 0, 0, 0, minus 1, and zeros. And finally 0, this gives me all zeros. If I do it the other way around, okay, now it's going to be complicated. 0, 0, 0, 0, 0, 0, zeros. This gives me all the zeros. Then this is a 0, and here I have a minus 1. Oh, that's not quite true, because it should be skew symmetric. Oh no, it's skew symmetric. And so what is it? It's exactly minus E3, right? And similarly, so now let's see this one. 0, 0, 0, 1, and 0, 0. This should all be zeros. 0, 0, 0, minus. Now the other way around. This on top gives me all the zeros. 0. Here comes the non-zero. No, let's see. 3. Now this is also 0. Finally, this one gives me the plus 1 here and zeros. So that would be E1. Finally, E2. E2 is. And finally, E2, E3. So we just have to get the signs right. E2, E3. Zeros. 0. Minus 1 here. And now the rest I don't really have to compute because there's more zeros. And the other one will give me the corresponding term here. Which is minus E1, I guess. Okay. Good. Not right? Physicists have computed these structural constants before. Probably many times. Yeah. Okay, now let's insert this. So let's see. When we want to compute the curvature for this Levi-Civita connection, right? So that's the Levi-Civita connection, which we call number 0 all the time. So, so for example, if I put an I here and 1 here. Okay, let's start slow. 1 here and 1 there too. 1, 1. Then this goes away, and this bracket is 0. Then I have a 1 here and a 1 here. So in order to get, can I get that? No, no matter what I bracket it with, will always give me 2 or 3. So if I multiply with 1, I get 0. Similarly, I have 1 here, 1 here. So no matter what I put in here, this will never give me a E1, so the scalar product will be 0. Right? Now, let's differentiate it in direction E2. Then I have E2 here and E1 here. And the only contribution, so let's see, E2, then I have E1, E2, which gives me minus E3 times E3 is minus 1, which gives me a plus 1 here. So that's plus E3. What I get here, so I have a 2 here and a 1 here. I can get this only if I insert, I have a 2 here and a 1 here. This gives me an E3 term. So this contributes on, no, let's see, JEI. I have a 2 here and a 1 here, so that's what we have. In order to get a 1 here, I need to insert the 3 here. And E1, E3 gives me plus E2 times E2 gives me a minus 1. Right? And finally, I have a 1, no, I have a 2 here and a 1 here. So I have to again to insert, the only way I get something will be E3 here. Then I have E1, E3, which gives me E2 times E2 is a minus 1. So we get that. Two times that. Because it is 2. And finally, can do the same thing by differentiating in direction E3. So let's just check. So I have E3, E1. So that means I have an E3 here and E1 here. The lead bracket of E3, E1, E3, E1 gives me minus E2. If this minus gives me plus E2, so if I insert plus E2 here, I get a plus E2. Now here I have what? I have E1 and E3 here, so I have to insert E2 here, the only contribution. And so I only get a multiple of E2 again. And what is it? It's E1, yes, E1, no, it's E2, E3, E2, which is plus E1 times E1 gives me minus. And here, again, this must be an E2. So then I have E1 here, E2 here, which gives me minus E3. That goes with minus gives me plus E3. So I get a plus. So plus E2. So that means I have differentiated the field E1 in all the 3 directions. Now let's see. From this, of course, we find that the coefficient matrix omega 1, 1, no, yeah, omega, if I insert E1 here, then the coefficient, and I have, let's say, 1 here, then these are all 0. So that's what I have. From this one, I have, if I insert an E2, and I have the 1 here, then I get one non-trivial contribution, namely when I have a 3 here, this gives me a minus 1. No, 1 is 1/2, sorry. Because of the factor of 2. And here, if I insert E3, I differentiate E1, then I get E2, so I have only one contribution here, and I only get 2, which gives me a plus 1/2. So that means the other ones, when I have an I here instead of 3 or 2, then they're all 0. So this is if I is equal to 3, 0 otherwise. And similarly here, I, this is 1/2 if I is equal to 2, and 0 otherwise. And so I have to keep computing. Now I have all the contributions with a 1. Oh. Okay, omega I2 of E2 will be 0 for the same reason as here. Then omega 2 I of E1. So this time I'm differentiating E1, but in the 2 direction. No, I'm differentiating E2, but in the E1 direction. So this is Q-symmetric. So when I put a 2 here, I get 0. So if I interchange it, I get also 0. So that means if this is a 1, I get certainly 0. And if it's a 2, I also get 0 because of Q-symmetry. So the only term that will not be 0 is when I is equal to 3. So we need omega 3, 2. So that's basically the last term I computed. So let's see what we get. Differentiating in E1. So okay. So this is a 1, that is a 2, so I have to have the 3 here. Okay, K has to be 3. Then I have E2, E1 is plus E3 times E3 gives 1, minus 1 gives a minus E3. And from this one, I have E1, E3, which gives me E2 times E2 is 1, minus 1 is minus E3. And here I have E2, E3, which gives me a minus E1 times E1 is minus 1 plus E3. So it's minus E3. And therefore, the coefficient in the expansion here of the E3 term is minus 1 divided by 2. It's minus 1. So, and finally, 3 terms. Also have 2, 3. Which is what? I2, 3, so that would be, so if I, for I equals 1, if I have a 1 here, then I insert E3, and this is having this 2 in here, but this gives me plus 1/2. If I interchange it, I get a sign. So it gives me minus 1. No, sorry. For I equals 1, yes. But that's this term. By putting I equals to 2 here. No, I'm not sure. But here, this term. If I put I equal to 2, then I have that term, which gives me, and by skew symmetry gives me minus 1. And now it's this I, so I'm always getting confused by that I and by this I. And 0 otherwise. Alright, and the last ones, omega 3I 1. Now what? Now we should be able to read them off by skew symmetry. So that is 1, so I have to take this form and I can put in an I3 here. So that would give me 0. I is equal to 1, if I is equal to, for I equals to 1. For I equals to 2, I have to use this one with I equals 3 here, which gives me that term with a minus sign. It's plus 1/2 for I equals to 0 otherwise. So minus 1/2, I get something, 0 otherwise. What is it? In this case, I have to take 2, which one I have to take? The one that I get is this one. If I put I equals 3 here, then I get minus 1/2. So then I get plus 1/2 here if this is 1. And finally, omega 3 pi. So now we have them all. Alright, so I write down the connection matrix. Omega is what? Now, let's see. For the 1-2 term, the 1-2 term is here I have the 1-2 term. Here I have the one, I can put I equals 1 here, and then I get only this contribution. So this gives me minus 1/2 times theta 1. Now the 1-3 term can be read off from here, and the only contribution the 1-2 term arises here and here also. Because then I get so that's a theta 3, right? And similarly, and so this way we proceed. So the 1-3 term I get from here by putting I equals 1, which I have to put I equals to 1. This gives me only this contribution, sorry. And here I have also to put I equals 1, and the only contribution that I get is this one, which gives me plus 1/2 theta 2. And so on. Now, and the only other term is this one, that is the 2-3 term. That would be here, the 2-3 term. And the only, when I put I equals to 2, I get this contribution here, plus 1/2 theta 1. I still symmetry these terms. Okay, and now we can compute everything, right? Because we have the omega, and then we can insert everything in the formula. That's the theta 3 here. The 1-2 term arises here with, no, the 1-2 term arises here with the theta 3, yes. Okay, anyway, so now one can insert this. So we have the omega. From this we can, so remember, the integrand that we were looking at is given by this formula that we derived last one, which I had on the blackboard today too. So it's given. So what we have to integrate is up to constant trace of omega, which the omega minus 2/3 omega cubed. And you can insert this and integrate over the manifold, which in this case is SO3. And then with this factor in front, so the factor C. And if you insert this, you multiply this out, you see, and then only the term containing the volume form enters, you get some multiple of the volume form. The volume form is such that it integrates to pi squared. This cancels the pi squared in this coefficient, and what you get after the computation is 1/2. What I want to mention before I finish for today, so now you see how a thing could be done. And the example 2 is a modification of the previous example. Again, n is SO3 as a manifold, but this time we use a metric which depends on the parameter lambda, and it is such that lambda times E1, comma E2 without lambda, E2 also without lambda, that's such that this is an orthogonal. Right, you could do that too. You have these 3 globally defined vector fields, declare those to be orthonormal, and then you can do the same computation. You just have to consider Lie brackets with this parameter lambda in front of the E1, so which gives you additional lambdas here in the formulas. And then you can compute the same thing, and then it turns out that the Chern-Simons invariant of SO3 with this metric G lambda is given by 2 lambda squared minus 1. So that's what we get. And here you see this is varying continuously in lambda, but there's no contradiction. It could be. And also this, if you let that lambda vary, you get all values of R modulo Z. So all values of R modulo Z can be taken as possible values of the Chern-Simons invariant. And so that's an example where things can be computed relatively explicitly because it's a Lie group, so that you can work with these globally defined vector fields, etc. Okay, so that's it for today. Thank you.